Okay, if we can start, perhaps if you can explain what meshing means in the context of data centers, that'd be a good place to start.
Okay. Um, well, meshing in the data center, especially in large hyperscale data centers, has been around for quite a long while. But as with a lot of things in our industry, there's lots of confusion around terms. So you can refer to a mesh network, could be a spinal leaf network, but here specifically we're talking about meshing of ports. So meshing of ports in a large data center, and you can do it in smaller enterprise data centers also, is basically taking a transceiver and splitting it out into individual lanes. So most common transceiver inside of a large data center would be what we call a DR4 transceiver, and smaller data centers or enterprise data centers might have SR4, which would be multimode based. But a DR4 transceiver will be 4 lanes of whatever speed you're running at. So if it was a 400 gig DR4 transceiver, you would actually have 4 physical lanes of 100 gig. And then meshing basically splits those 4 lanes of 100 gig and splits them across 4 separate ports on the far end. So you take lane one on one end, on end A, would go to MPO1 on end B. So you would take 4 MPOs on one end, and lane one from each of those 4 MPOs of 4 transceivers would go to MPO1, and then lane 2 would go to MPO2, lane 3 goes to MPO3, and lane 4 from each of the 4 MPOs goes to MPO4. So it's basically just creating a 4x4 mesh. And it's 4x4 for a DR4 transceiver. If you were going at 800 gig, you might have either a DR8 transceiver or 2x DR4, in which case you're meshing either 2 4-lane transceivers, or you would mesh 1 8-lane transceiver. So fundamentally, the end result is it takes 4 lanes from a single port and splits that across 4 individual ports on the far end, allowing you to split one single port across 4 ports on 4 separate switches, which could then be on 4 separate, what we call fabrics in the data center, where a fabric is a isolated standalone network in the data center.
Okay, and the world has gone, shall we say, AI crazy to a certain extent, and in terms of the data center, they've caught the bug as well, if you like. So it'd be good to understand why is meshing particularly important for the GPU intensive AI compute workloads that we're seeing, which are growing and growing. Why is meshing so important in the AI world?
Yeah, as I said, meshing has been around for years, but historically, meshing has been around for what we call increasing the radix or the reach of the data center. So, for example, the easiest way to think of it is if you have a 32-port switch in the data center, well, then you can connect a single device to each of those ports. So a single switch with 32 ports will be able to connect to 32 devices. If you then take your DR4 transceiver and you split it out into the 4 lanes, so then each of those 32 ports has 4 lanes. So you increase the reach or the radix of the switch from 32 to the 128 lanes, allowing you to connect a single switch to 128 devices. However, that's traditionally in a kind of a mesh and kind of meshing the ports. In AI, it's a slightly different, very similar principle, but slightly different. The main reason in AI is to create, if you have 4 lanes, you create what we call 4 planes in the AI network, where each plane is a separate fabric. So the separate fabric then allows the one single port to transmit on 4 fabrics or 4 separate networks at the same time. And the reason you do that is because in an AI network, you have tens of thousands or hundreds of thousands. So an AI cluster, even 12, 18 months ago, an AI cluster, a big cluster was 16 or 32,000 GPUs. Now we're getting to large clusters with 150,000 GPUs. Not all of those 150,000 GPUs are going to be transmitting at the same time, but the way that the AI cluster, the GPU cluster works is a bunch of the GPUs work on one part of the problem, they solve that part of the problem, and then they pass it off to the next bunch of GPUs. But when a bunch of GPUs, which could be hundreds, could be thousands, pass off that workload to the next one, it has to pass in one single data transmission. So an AI network fundamentally has to be what we call lossless. So the early AI networks were based around InfiniBand, because InfiniBand has always been lossless. So you transmit, it has an address it goes to, and in InfiniBand, it does this handshake before it transmits. So if I'm sending something to you, I go, Phil, are you ready for this? And you go, yep, I'm ready. And then I send it, and it goes to you, and you receive it. In Ethernet, it doesn't matter what's between you and me. If I send it to someone else and goes to someone else and eventually comes to you, I just send it. And then if it collides or crashes or it doesn't get to you, I get an error message back, and then I retransmit it. In an AI network, if there is a collision or a crash and a data packet doesn't get delivered, then the whole workload falls over and it has to be redone again. So it has to be lossless. So in order to make it lossless, we create these planes or these 4 different routes, and then the new Ethernet protocols will ensure the path is clear, or will take the least congested path, and it will send it over that path in order to create this lossless Ethernet. So Ethernet has been is designed as a lossy protocol, lossy in that it loses packets and it doesn't really matter. It kind of it has this collision detection, retransmits, and everything's fine. But for an AI workload, you can't have those losses, and that's why InfiniBand at the beginning was used. And people don't like using InfiniBand because it's it used to be the InfiniBand consortium, the OIC, I think it was called, and it was largely Mellanox were driving it. Recent years, NVIDIA bought Mellanox, and InfiniBand now is sole source from NVIDIA. So if people are buying all of the GPUs, because NVIDIA are the leader in the GPUs, and they have to buy all their InfiniBand switches, it's not ideal. People want to use Ethernet, they're used to Ethernet, but it has led to this new form of Ethernet called RDMA over converged Ethernet, or ROCE. And there's a lot of work going on in there's the Ultra Ethernet Consortium, who are developing new protocols for transmitting lossless Ethernet. So that's kind of the why meshing is to create these different fabrics and allow a lossless transmission. So the easiest way to think of it is if you think about a road network. So if you're driving from London up to Birmingham, you basically got loads of different routes. But let's say there was 4 different motorway routes that you could take. Then before you set off on your trip up to from London to Birmingham or Manchester, it doesn't matter where the hell you're going. Before you set off, you look on your Google Maps and you go, this is the least congested route, I'll go that route. And that's exactly what it does. So the RDMA over converged Ethernet, this ROCE, that's your Google Maps, and it says this path or this network or this fabric, in the case of a data center, is the least congested. If we send it this way, it'll get through.
Okay, and in terms of the sort of strategies or approaches used when it comes to implementing meshing in a data center, what are they, and are any of them more suited to this AI world that you've been describing, or are they all equally suitable?
Yeah, it's I mean, that's a mesh could be a 2x2 mesh where you're creating 2 planes. It could be a 4x4 mesh where you're creating 4 planes. It could be an 8x8 where you're creating 8 planes, or 16 planes, depending on what you need. The kind of normal in a large AI data center now, large being anything from 50,000 to 100,000 to 150,000. Well, anything above 100,000 is extremely large. That'd be an AI factory. But if we focus on a 4x4, which is pretty standard, All you're doing there with a 4x4 mesh is you're taking a four DR4 ports, whether they're 100 gig, which would be 4 lanes of 25 gig, or 400 gig, which would be 4 lanes of 100 gig, or 800 gig. And 800 gig is generally what they call 2x DR4. So it's 2 separate sets of 400 gig, each with 4 lanes of 100 gig. So if you have a 32 port 800 gig 2x DR4, then those 32 ports effectively become 64 ports of DR4 with 400 gig. So if you have the 4 lanes and you're doing a 4x4 mesh, then the still the standard in the transceiver is for an MPO an MPO8 for a DR4 transceiver. It could be in the future could go to an MMC. It could be an MPO16. But if we focus at the moment on MPO8, so the MPO8 has 8 fibers, which is 4 pairs of transmit and receive. So let's just call if we could forget about the fibers and we talk about lanes. So a lane is a transmit and receive pair. So you got one MPO on end A has lane 1, lane 2, lane 3, lane 4. And what you want to do on the mesh fundamentally is you take that one MPO at the far end. It would go to, so lane 1 would go to MPO1, lane 2 would go to MPO2, lane 3 goes to MPO3, and lane 4 goes to MPO4. And then for your MPO2, that splits across the 4 as well. So what you end up with is on end A, you've got lane 1 to 4 on each of 4 MPOs. And on end B, your first MPO has 4 lane 1s, the second MPO has 4 lane 2s, the third MPO has 4 lane 3s, the fourth MPO has 4 lane 4s. That's quite a mouthful to get out.
Yes,
but so it basically just allows, so fundamentally then you end up with that the first MPO on end A goes to 4 separate MPOs on end B with lane 1 or lane 1 and 1, lane 2 and the other, lane 3 and then lane 4, which then allows those 4 MPOs on end B to plug into 4 separate switches on the far end. And those 4 separate switches would be the first layer. If you're coming from the GPU to the first layer of switching, that's the 4 separate switches are the 4 different fabrics, or the 4 different, basically you're coming out of your house, it's coming out of the GPU, and you're putting one lane on one road going up to Birmingham, one lane on another road going to Birmingham, another lane on the other road, and the 4th lane on the 4th road. So you get all of those lanes set up. And then when you transmit the traffic, i.e. when you drive off, then your Google Maps or your RDMA over Converged Ethernet decides which lane you're going to take. So it just allows that splitting of the fabric across the 4 options in the fabrics. And then kind of that's fundamentally what you're trying to achieve. So all you're trying to achieve is 4 MPOs to 4 MPOs, and then you have this mesh shuffle in the middle, which we do in the factory. And then how you physically do it in the data center, there are numerous ways. The original way and the way that NVIDIA recommend is what they call a shuffle box. So it's basically like an MPO patch panel, and it would have multiples of 4 MPOs in and 4 MPOs out. So basically you go into the box, there's a big shuffle of fibers inside the box, and then you come out with the MPOs based on lanes. So 4 lane 1s in one MPO, lane 2s in the second, lane 3s in the third, and 4s in the fourth. So that's a shuffle box. That's a good solution for a small cluster. It has its drawbacks. It adds 2 extra connectors in the channel, adds a huge amount of space for in the patch racks, because you're talking thousands and thousands and thousands, hundreds of thousands of ports for in a big AI network. So you've got to add an extra 2 connections for each one. It takes a huge amount of real estate. So it's not an ideal situation. It's probably the simplest, easiest, because you can stop it, but it adds loss, cost, and space. Then the most simple way to do it is you're going to connect your trunk that runs down the data center. In order to connect to your switch, you're going to use a patch cord. So instead of using a single MPO to MPO patch cord, you use a 4 MPO to 4 MPO patch cord. So it's exactly the same, except you're connecting 4 ports at a time, and you do the shuffle in the cable. So that's what we call a shuffle patch cord. So it's just, and you wouldn't notice any difference. It would be exactly the same as a normal 4 to 4 32 fiber patch cord. That's the simplest to do. You could also do what we call a shuffle trunk. So shuffle trunk could be it could be 128 fibers, could be 256 fibers. But if you're doing a 4x4 shuffle, it'll be some multiple of 32 fibers. So if you're coming, for example, from a GPU rack going up to like a T0 switch in the same row, you could do a shuffle patch cord, or you could run a shuffle patch cord across or a shuffle trunk, sorry, across the data center. But if you do that, then if the infrastructure changes in 2 years, you're kind of stuck with a non-standard trunk running through the data center, which is never a good idea. You want to keep your permanent infrastructure as standard as possible, but if you're running within the same row, you can kind of put the shuffle in there. And then the last one we use is what we call a multi-shuffle patch cord. So this would only be in the same row. So it would only be really between a GPU rack and a T0 switch, where you just take, it's literally, instead of the shuffle patch cord, it's multiple shuffle patch cords. So you would have a 64 or 96 or 128 or 160. But basically it's just for the shuffles in the same cable. And when you're running the latest NVIDIA NVL72, the GB300, there you're generally running 1152 fibers between the GPU rack and the T0 switch. So kind of bundling all of the patch cords, well, not bundling, but making multiple patch cords in the same cable saves a huge amount of space and weight in the basket. So doing a multi-shuffle patch cord running down the row is the most efficient and the most common we see in the large hyperscale data centers.
Okay, and just apologies if it's a silly question, but with using your analogy, getting to London to Birmingham, 4 options and you choose the fastest. Are you not able with AI workloads to go, we'll actually send them on all 4 routes and assemble them to me, in Birmingham? That's not possible with AI. You have to go down one single route in effect. Is that right?
No, it can choose all 4. It can choose 2. The key is it'll predict congestion, and it's literally, the congestion is exactly like traffic on the road, and it'll avoid. But the risk is if you send it down 2 paths or 3 paths or 4 paths, they have to get retimed, and that's where Ethernet again has a drawback from InfiniBand. You have to do this retiming, and you have to make sure that they do go down the same path. They're riding at the same time, but generally it will split and choose one of the paths, which is the least congested.
No, thanks for that. I guess the question with the way AI is developing at a rapid pace, how do you see meshing evolving over the next 3 to 5 years to sort of cope with what AI is going to be doing? I know, I mean, from my data center, we're looking at the 1 megawatt rack, so goodness knows alone how much hardware that's going to be supporting. So yeah, how does meshing cope with what AI is going to demand of it over the next few years?
Well, the meshing sounds complicated, and people kind of, the amount of customers, I'm talking large hyperscalers, I've spoken to, where they've initially requested a mesh box, and then I explain a mesh cable to them, or a mesh patch cord, or a mesh trunk, and they go, "Oh, that sounds complicated." I'm like, "Well, it is complicated, but that's down to us to work that out. You just order a cable, we'll deliver it, it'll work, we know how to do it, and we've mastered it." So it's kind of it has become more commonplace. We make thousands of these things every week, and no issues. But I do think moving forward, I mentioned the kind of new generations of Ethernet. So there was one particular project we were working on in the US for one of the hyperscalers, and they were waiting for these developments on Ethernet, and they had planned to build the data center originally on InfiniBand, and it got to a stage that they wanted to install 2 separate fiber infrastructure networks in the data center, one that would be able to run InfiniBand and the other one with meshing that would be able to run Ethernet. And because they were waiting for this development of Ethernet, and the Ethernet came eventually, and they were able to just do the meshing network, which was their strong preference. So it's kind of the evolution in Ethernet is happening really, really quickly. So I think probably the most likely solution to move away from meshing is that there's a consortium now called the Ultra Ethernet Consortium, and they're working on next generations of RDMA over converged Ethernet. So RDMA is it's remote direct memory access. So it's an addressing method of sending packets, and it has this handoff and this kind of confirmation before sending. So it's probably the most likely is that the Ultra Ethernet Consortium come up with solutions that don't require meshing, that has this handoff before packets are sent. Another option could be kind of we're starting to see and hear talk about co-packaged optics inside of the data center. So if it's a co-packaged optics, it means that currently the electrical to optical signal is done at the transceiver. If the electrical to optical is done at the chip, then between the chip and the front plate of the switch is literally a small fiber patch cord. So you could, between the chip and the front plate of the switch, you could do the mesh inside of the switch. So then once it arrives on site, there's no concern for meshing. But ultimately, I think we'll see meshing and mesh cables, mesh panels, mesh trunks in the data center, I think, for the next 3 to 5 years. And then optics will change, switches will change, and my prediction will be that the need for meshing will go away with the advances of the Ultra Ethernet Consortium.
Okay, but I guess one of the important messages, bearing in mind, you mentioned there, I think the potential of silicon photonics and what people maybe call optical computing. Bearing in mind that and the landscape you've already described, open technology sounds pretty important. Now, you obviously said NVIDIA in InfiniBand, works well, but at some stage, I guess NVIDIA and GPUs will get replaced, or there will be competition for them, and therefore openness via this Ethernet approach is you think is pretty important for people to at least bear in mind whether or not they choose to go that route.
Yeah, I think that's the reason why. So meshing, people kind of view meshing as a complexity, and it should be a complexity that we AFL deal with. The customer shouldn't see anything around the meshing, and we should make it completely seamless, so it doesn't add extra connectors in the link, so it doesn't add extra real estate in patch panels and etc. So we manage it, and so but people. In using Ethernet in the data center, the drawback is you have to mesh it. If you go with InfiniBand, you don't have to mesh it, but the drawback is you're tied purely to NVIDIA. And people, I think, and also if you take a network engineer who's been doing Ethernet his entire career, and you say to them now go and configure and troubleshoot InfiniBand, they kind of have a bit of fear around that. So I think the strong desire is to stick with Ethernet. It's kind of Ethernet is the 99.9% standard inside of a data center. InfiniBand has always been there in high performance compute clusters, purely because of this whole shifting of entire workload and huge chunks of data. So I think the desire is definitely to have Ethernet. The desire is to have open source. I mean, if you take the hyperscalers, they haven't bought branded switches for a long time. They'll buy switches from Acton or from EdgeCore or whoever, who are kind of bare metal switches that don't even come with an operating system, and then they have their own operating systems. So they don't want to go back to a kind of a branded kind of a whether it's NVIDIA, whether it's Cisco, whoever it is, they want to kind of, and they've also over the years, different hyperscalers have done different things with different switches. So none of them would have a standard, let's call it Ethernet switch, because they adapt the switches and the Ethernet protocol that's running on it to be very specific for their needs. So they need that kind of open choice. And even on that, the main difference between when NVIDIA brought out their NVL72, it was with the referred to as the Grace Blackwell 200, or the GB200. And then pretty soon after they actually released it, they changed it to a GB300. And the fundamental biggest difference between the 200 and the 300 was that the 200 was sold as a full NVIDIA stack. So it was the NVL 72, 72 GPUs, had their NVL switch in it, and it was a single SKU, buy that whole rack, 130 megawatts, water cooled, wallop, that's it. And then for the GB300, with pressure from the market, they brought it down and chunked it. So if you wanted to buy just a GB200 or GB300 tray, you buy the tray. If you want to buy just the NVLink switch, you buy the NVLink switch. So they kind of disaggregated the rack because of market pressure. So I think there is, to your point, there is a desire so for any of the hyperscalers to buy components of the NVL 72 and put that into their own systems. So yeah, I think people don't like their hands being tied, and that I think is the biggest challenge for InfiniBand.
Okay, it's been fantastic to chat, and thank you so much for sharing so many great insights into what is going on in the world of AI as it relates to the computing inside the data center. So, Keith, really appreciate your time. Thank you.
Cool. And if you want more info, there's we've literally just finished writing a white paper on meshing. So on the site aflhyperscale.com, and a paper there along with a lot of other recent white papers around AI meshing and what it all is. Thank
Lovely.
you.
Thanks again.